And to our guest, this is what I will do. If you think this technology is new, it's as old as me. And I brought an example of a self-driving car from 1956.
Whoa!
I wanted to show you the video. I have it queued up. It's from the GM Heritage Collection. It's only a minute long, but I think it'll crack you guys up because of all the technology that was already working in 1956. We'll cue it up. We tested the sound. I'm going to turn it down.
A milestone in automotive engineering is marked by the completion of General Motors' Arbor II turbine family car ever built and tested in the United States. Progress made possible by the pioneering of the original.
Oh, you haven't seen it. Excuse me. 1 second.
I thought it was a great.
No. We love our technology. It gives me endless reasons to cuss. Okay? 1 second. Can you see it now?
Yes.
It'll be more fun if you can see it, right? 1 second.
Automotive engineering is marked by the completion of General Motors' Firebird II, the first gas turbine family car ever built and tested in the United States. Built by the pioneering of the original Firebird. Now, gas turbine engine can be harnessed for cars and trucks. So using great power in small packages. New generator, exhaust heat is no longer a problem. Though the experimental car of tomorrow has a science fiction appearance, it is practical and usable in every design. Even the electronic safety highway is feasible for the future. Here, tomorrow's driver might just push a button, and the car would literally drive itself. Its electronic receivers would pick up various impulses and roll it along in complete safety. A TV screen reveals pertinent travel information and gives highway and weather reports. Following these test runs, she hedged the motor around, matching the car with the road. The research men of General Motors seek complete comfort. This laboratory on wheels not only runs on the safety autoway, but can be manually operated and driven, as it is here in the hills of Arizona. This may well be part of the American scene in 1976.
There's a lot more on the website about this, but it had a picnic table, amongst other things. And I'm going to turn over to the next person who's going to speak, if you are ready.
All right.
Thank you so much.
Thank you.
Yeah, so my name is Alex Polanski, and I'm from the Detroit Autonomous Vehicle Group. Thank you everybody for coming out, and thank you University of Michigan, Mcity, Udacity for organizing the event. I think this is an awesome opportunity, and it's great to have so many people in one place. And so, David Silver, thank you for coming out all the way out here. Much appreciated, and the team for helping with everything. Also, Jim Sayer, who helped organize the event and take everybody on the tour. Very cool, very kind. I don't know how many of you have been there before, but it was the first track, and it's awesome to see how the technology is progressing and what's helping it progress. Thank you, David, for helping, coming out from Ann Arbor and organize. I think it's a very exciting time for the technology, and we can help shape the future. And so we will, in a second, have David Silver come up, but David will also say a few words. But thank you for coming out.
Yeah, and ditto, thank you guys so much for coming out. When Alex and I started kind of tossing the ball back and forth, thinking about this event, part of what the Detroit group and the Ann Arbor group are about community, and it's just, getting people like you guys together. We sensed there was some energy out there, and then it really came together, and this is, testimony to that fact. So thank you guys very much for coming out. So we'll have a little bit on Udacity, and thank you guys again from Udacity, because we wouldn't really be here if it weren't for Udacity. If you don't know about Udacity, check it out. They're rocking the educational world, and the enlightenment world is what I tell You don't have to be in grad school to take their courses. All sorts of people can do it. It's amazing. It's a whole new paradigm. So super stoked that they came out. The Ann Arbor group is going to be involving, if you guys, there's a lot of us here that are in the Detroit or Ann Arbor Autonomous Vehicle Group where we're building a car and we're going to have a competition. If you're at all interested, I'd encourage you guys to check those groups. Speak to Alex, speak to me. There's a lot of people here from both groups today with the red hood and Bram sitting next to him. So I encourage you to talk to these people if you want to talk about technology. Those are the guys. Daniel's back here, another great technical resource. So with that, I think we can slowly segue over to David Silver. And again, thank you guys, because this is what it's about. It's making that community. It's not just behind the podium in the classroom. It's out on the streets with people hacking and doing hack fests and stuff like that.
Cool. Thank you so much. Hello, everybody. Thanks so much for having us here tonight. My name is David Silver. I am the head of self-driving cars at Udacity. David was kind enough to introduce us. We are an online education company. We offer a variety of classes online, mainly related to software engineering, and I teach our self-driving car nano-degree program, which trains software engineers to work on autonomous vehicles. I definitely see some folks I know who are in the program or familiar with Udacity. Who here is in the self-driving car program or has taken the Udacity class and knows about Udacity? Okay, all right, so like half the room. All right, well, I'll share with you a little bit about how the nano degree program works. Hopefully it won't bore too many of you who are already in the program, and it'll be fairly quick, and at the end we can talk just about self-driving cars, and can ask me anything you want about Silicon Valley, about Udacity, about me, about anything that comes to mind, and I'll do my best to answer. So I came to Udacity about a year and a half ago from Ford Motor Company, and I have my own kind of interesting backstory. I was for many years a normal Silicon Valley web software engineer. Does anybody know what the red icon there is? Ruby. All right, everybody. A lot of rooms I go into, nobody knows what that is. I'm a Rails engineer for many years. And a few years ago, I got really excited about self-driving cars, but I didn't have any background in automotive software or in robotics. I was online at Udacity and in other places. And I was fortunate enough to be able to get a job on the autonomous vehicle team at Ford in their Palo Alto Research and Innovation Center. And the folks at Udacity saw what I had done, and they asked if I could come to Udacity and build out a path for other people to do essentially what I had done for myself, a path into the autonomous vehicle industry. So I've been at Udacity since last summer, building the program. We've had about 10,000 students all around the world enroll in the program so far. About 50% from the US. I would guess about 5 to 10% from the Detroit area. This is one of our largest concentrations of students. And we have a number of graduates, including a few people in this room, I think, who have gone on to work in the autonomous vehicle industry. So if you're interested, you can network after I finish talking and then figure out how they got their own jobs in self-driving cars. I think it's a really fun space to work in. Udacity is kind of an interesting company in that it was founded by a man named Sebastian Thrun. Who here knows who Sebastian is? Ring any bells? All right, again, it's a good crowd. So Sebastian is quite an accomplished guy. He founded Udacity about 6 years ago, but before that, he was the founder of the Google self-driving car project, now Waymo. He spent about 6 or 7 years at Google, building out first Google Street View and then the self-driving car project. Prior to that, he was a professor at Stanford University, where he led the team that won the Arbor Grand Challenge, which was a 100-mile-long self-driving car race through the Mojave Desert. Back in 2005, I think, they kind of kicked off the self-driving car boom. So he has kind of a foot in the self-driving car world as the father of self-driving cars, and a foot in the education world, both as a at Stanford and then the founder of Udacity, which offers all these online courses. And it's a real honor and pleasure for me to get to work with him, kind of combining those interests, building a self-driving car program. So I'll take you through the program a little bit. This will be familiar to those of you who have enrolled or are familiar with the program. And I'll kind of point out the ways in which the program was designed to mirror how data flows through a self-driving car, and kind of how this informs maybe how self-driving cars work. So we start out with an introduction, just kind of what are self-driving cars, how do they work, and then the second month of the program is deep learning, and the third month is computer vision. And both of these topics really have to do with cameras. Deep learning can be applied to a whole variety of things, but for self-driving cars at the moment, they're primarily applied to camera images, video feeds. Computer vision is kind of classically how do we take camera images and figure out what the world looks like. And Jim Sarah was talking about that a little bit. I heard them talking about the nav shuttle. They rely primarily on LiDAR to figure out what the world around them is. They do a little bit of image processing. Image processing is sometimes a little bit of a synonym for computer vision. So in our deep learning program, students learn to build deep neural networks to do things like classify traffic signs, and even in simulation to do something called behavioral cloning, which is where you train a deep neural network to drive like a human driver. Typically in self-driving cars, we think about breaking the problem up into chunks. So you have a chunk that finds and detects and classifies traffic signs and traffic lights, and another chunk that figures out how to turn the steering wheel, and another chunk that figures out how to route your car through the world. End-to-end learning or behavioral cloning is this kind of advanced technique for self-driving cars where you teach a car or a neural network to drive just by watching humans. So the neural network doesn't have to learn to do anything in the middle. It just watches when a human turns the car left, when a human turns the car right, when a human hits the brake or the throttle, and just mimics that over time. And with enough training data, potentially it can learn to actually drive simply by seeing the same things that a human sees. One of our partners, NVIDIA, is doing a lot of work in this area. NVIDIA creates GPUs, graphical processing units, built for deep learning. Deep neural networks are essentially these tools that are amalgamations or layers of artificial neurons, which is just it's all bits and bytes, but it's a conceptual framework for how data would flow through a network. And if you think about how GPUs or what GPUs are designed to do, they're essentially designed to put data onto a screen, and they're designed to change thousands of pixels on the screen kind of all at the same time. And training a neural network is kind of doing the same thing with neurons. It's running the same calculations with thousands and thousands of these artificial neurons in the network all at the same time. So NVIDIA has become really important in that field, and they actually teach some of their end-to-end learning research that they're doing to students in the course. Our computer vision module deals with kind of what you might think of as more standard computer vision. That's how to use color spaces or lines to do things like find lane lines on the road or detect other vehicles. There are lots of different ways you can transform an image that can help a computer extract more data from that image and figure out where the interesting things are. So that's all of what we consider the first term of the NANO degree. The NANO degree is 9 months, broken up into 3 terms of 3 months each. I'll show you one of the videos from one of our student projects. So this is one of our students, his name is Dab. I've been using this video forever. Probably found a new one, but he is using here both standard computer vision, which he uses to find the lane lines, things like colors and lines in the image, and then he's trained a neural network to detect vehicles and draw that lane bounding box around the vehicle on the road. And his lane finding algorithm is particularly impressive because you can see the car just drove over a bridge, the color of the pavement changed, the lines are curving, and yet the lane lines are still really, really robust. And you can see this interesting thing happening here with this neural network where 2 cars kind of overlap each other and one occludes the other, and the neural network is trying to figure out, is that 1 car, is that 2 cars? Eventually they separate and it figures out what's going on. But this is, pretty advanced stuff. This is similar to what you might see in a pretty high-end ADAS system. And this is the type of stuff students in the program get to do in the first few months of the nanodegree programming. So it's kind of amazing what you can do online anywhere in the world nowadays with a video of us driving on the highway in California. So the second term of the nanodegree program is what you might think of as more hardcore robotics. This is sensor fusion, localization, and control. So the first term, we were looking largely at camera images. So we're using camera images to figure out what the world around us looks like. You'll have noticed that the Navia vehicles out there and any other autonomous vehicles you might have seen, most of them will have LiDARs on them. They were these little pucks that were on top of the Navia vehicles, shaped a little differently than pucks. These LiDARs are essentially laser beams. They're rotating laser beams that ping out into the world and then bounce back. And the computer uses these pings out into the world to construct what's called a point cloud. And that has some advantages over camera data and some disadvantages. And similarly, radar signatures have advantages and disadvantages. For example, cameras are much better for classifying objects. They're really the only way to figure out whether a traffic light is red, green, or yellow. But lasers are much better at determining how far away something is. Determining distance and velocity with camera data is notoriously difficult, but lasers and radar are really accurate with that. And so we use a domain called sensor fusion to kind of fuse all this data together, both data from multiple sensors and data from the same sensor over time, to get a sense of what is the environment around us, what does that look like. So now we have data from the camera, and we have data from radar and lasers, LiDARs, and we fused all that together to get this kind of comprehensive picture of what does our environment look like. And once we kind of got that picture, the next step is to figure out where we are in that world. So we kind of know what the world looks like, and now we need to know where we are. Jim talked about this a little bit out on the test track. He talked about how when it snows really hard, the vehicles can't figure out, or they can't even see the lane lines. They can't necessarily even see the curves. They don't know exactly where they are, so they're looking for landmarks. And they're trying to localize themselves to those landmarks. They're trying to figure out where am I in the world. Typically, they do this with high-definition maps. So a place like Mcity will be mapped really, really well. And as the self-driving car drives through Mcity or through whatever environment it's in, it will try and figure out, there's a lamppost, there's a traffic sign, there's a trash can, and it will try and localize itself to those landmarks so that it doesn't drive off the road. You might think, we all have GPS on our phones now, we all kind of know where we are, and that's true, but in fact, GPS is only good or only accurate to within about 1 to 2 meters. Think about how big 1 to 2 meters is. If the car is off or wrong about where it is by 1 to 2 meters, it will be off on the sidewalk hitting things, and that would be really bad. So we use much more sophisticated localization techniques, sometimes things called particle filters, other mathematical techniques, to figure out where we are in the world, essentially really sophisticated triangulation. The next month of the program is something called control. This is a really classical domain of automotive engineering. This is how you actually turn the steering wheel and hit the throttle and hit the brake to move the vehicle through the world. So if you think about like making a left turn, I know I often make left turns and I have this vision of where I'm going to drive the car through the turn, and I still sometimes like understeer or oversteer, and a car or a computer kind of does the same thing. It projects where it wants to go, and then it figures out how to turn the steering wheel and the throttle and hit the brake to execute that. And this is something that's been around for a long time in things like cruise control. Now there is adaptive cruise control, which kind of does the same thing. How do I get to 70 miles an hour or 60 miles an hour on the highway? Sometimes you might overshoot it, undershoot it. You use a controller to make sure you hold the speed or the trajectory that you're looking for. So this is another one of our students, a project from the nanodegree program. This is a model predictive control project. This is using one of the Udacity simulators we built for the program. It's like a video game. And what you can see here is there's a car, there's a yellow line, which is the line that we'd like the car to drive. And then there's a green line, that's the line that the car is actually driving. And the student's goal in this project is to build that green line so that it overlaps with the yellow line as much as possible. And you can basically think of that as driving down the road, and you have this image in your head of the line that you'd like your car to follow, and you're trying to turn the steering wheel and the throttle and the brake to follow that line you're imagining on the road as well as you can. Use fairly sophisticated control techniques and optimization techniques to accomplish that in the program. So that's the second term, and now we're in the third term, which is kind of the end of the program. We cover path planning. So this is how we figure out what trajectory of paths to actually take through the world. So in order to have something to hand to that controller to say, follow this line, you actually have to build the hypothetical line first. Maybe the hardest question in autonomous vehicles right now, or the hardest problem, is how do you build path planning, particularly for things like urban driving. There are a lot of steps involved. Typically, you want to look at the vehicles around you and the bicycles and pedestrians around you and project out into the future. What do you think those vehicles and pedestrians and bicycles and other objects are going to do in the future in the next few time steps? And then you want to figure out yourself how do you want to react given what you think the future will look like and given where you want to be with your vehicle or where you want to go. And then finally, you actually have to build the line to execute whatever maneuver you want to take, whether that's simply holding your current trajectory or shifting lanes left or shifting lanes left or shifting right or turning left, turning right, coming to a stop. So that's path planning. The 8th month of the program is an elective month where students can take one of a few different topics. One topic is advanced deep learning, so doing more with deep neural networks and using them to find free space on the road and figure out where you can drive that you won't hit anything. Another is functional safety, which is a pretty important topic in standard automotive engineering, which is how do you verify that the code that you're writing or the code you're designing does what you think it's going to do and is acceptably safe. And then the final month is system integration, which is where students bring everything together and get a Udacity self-driving car, a car that we have in our own parking lot in California to drive. So we have this car in California, and our students are all over the world. And in the final month of the program, they form teams of about 5 students, and they build the code to drive the Udacity self-driving car. We have a simulator that we built especially for this. Students, and the students write their code, they run it on their own computers in our simulator, and then they send the code to us. We double check, we run the code in the same simulator on our own computers, make sure that the code isn't going to crash anything. Sometimes we send it back. But if everything works, then we put it on our car and we drive it around our test track. So you'll see that in a second. So first, this is path planning projects, and you can see this is another one of our Udacity simulators. And essentially, this car is doing highway driving, and it's trying to navigate through traffic to get where it's going, and it's subject to constraints, just like cars in the real world would be subject to. So it has to adhere to a speed limit, it has to adhere to an acceleration limit, it has to adhere to something called a jerk limit, which is essentially not accelerating too fast or too slowly. And this car has these green pearls in front of it, which are the waypoints. And what the student is building is this path, this trajectory that the car should follow, is putting these green waypoints in front of the car, and then the car follows those waypoints and navigates through traffic. This is, I think, probably the hardest, or at least most open-ended problem in self-driving cars now. It's fairly well understood how you might build a system like this on the highway. Building a system like this for urban driving is the big challenge that a lot of top OEMs and technology companies and auto suppliers are working on at the moment. And
There we have a red light and a danger red light water.
this is one of our student teams running the code on our vehicle.
Sorry. Stop here for a second. No, it's not. Great. Yes, thank you. moving slowly around the track. I hear a little bit of something to do with the throttle and the brakes. I'm not quite sure, but I don't feel any ride as far. And that's the end of the waypoints that we have set up for the track. Nice work.
All right, so what you'll see there is we do not have Mcity at our disposal. We have a small parking lot at a nearby organization that lets us borrow their facility during the week. And we do have one traffic light that we've set up, so you might have noticed the car, when it first starts, it comes up to the traffic light, it has to stop when the traffic light turns red, and then go again when the traffic light turns green. That's actually a surprisingly difficult thing to do, simply because figuring out where the traffic light is and pulling it out from all the other things in the image is a little bit difficult. But this particular team, their code found the traffic light, it stopped. When the traffic light turned green, they went and they followed a loop around the parking lot, just like they were supposed to, and came to a stop at the end. So that's kind of the culmination of the whole experience is building code to run Carla, Udacity self-driving car in Palo Alto. Udacity does all sorts of stuff. These are some other programs we run: machine learning, artificial intelligence, web development, front-end web development, data analysis, marketing, or digital marketing, design thinking. But I, of course, am most excited about our self-driving car program. And if you haven't checked it out, I encourage you to. And if you have any questions about self-driving cars or anything else, I am happy to talk about us, about California, Silicon Valley, autonomous vehicles, the future, me, anything. So we can.
One question that I have: what's your interface? What kind of automobile is that?
Great question. So the question is how do we interface with that particular car that you saw in the video? So it's a little bit of a longer story, and if you bear with me, I'll kind of tell you the story of that vehicle, of Carla. That is a Lincoln MKZ, essentially a souped-up Ford Fusion, that we bought from a company called Autonomous Stuff, based out of Illinois. And what Autonomous Stuff does is they sell vehicles that are what's called drive-by-wire. So they don't make self-driving cars, but they do give you a vehicle that you can program to drive. So they essentially drove that car to our office, a video game controller, just like some of you might have seen in the Navia vehicles, they also have a video game controller. And they said, look, you can drive the car with the video game controller. And we could, in fact, sit in the car and drive it with the video game controller. And they said, if you can drive it with the video game controller, you can program a computer to drive it. Now it's your job to program the computer. So from there, we loaded up the computer that they put in the trunk with Linux, and then on top of that, something called ROS, which is Robot Operating System. That's a little bit of a misnomer. It's not actually an operating system. It's it's like a middleware package that processes messages across different parts of the robotic system. And then on top of ROS, something called Autoware, another open source package that does more automotive-specific work, including localization. And then on top of that, we wrote our own code to do things like stop the traffic light and follow the car around with them. So that's how we interface with our car. Our code and Autoware and ROS and Linux, and then at the bottom is this drive-by-wire car that we got. Yeah.
What is it called the application? Is it cross-CNN or Google?
So for object detection in Carla right now, it's up to the students what they want to do. We teach a couple of different fully connected networks in our, fully convolutional networks in our advanced module, or excuse me, our advanced learning module in the program. I believe we teach SCN on top of MobileNet. For obstacle detection, we actually don't have robot obstacle detection set up in the vehicle right now. It's not part of the capstone project that we put on the car. There's no avoid. We have done obstacle detection more kind of for our own work and to see if we can do it. our signature. So we have to figure out if we're getting feedback from the radar, and is there a base optical detection, or fidelity, if we see something ahead of us, we slow down.
Do you have a certain course that can handle the low level stuff?
Yeah, good question. So do we have courses that teach essentially how to hack the car, or at least what goes on the lower level parts of the vehicle? We don't. We focus more on the higher level for a couple reasons. One, there tend to be more jobs in that area. We actually very jobs focused. Fairly well understood how to program a car to be driven by wire. The hard part is that the OEMs all lock that down and essentially make it a secret. They don't necessarily want to sell cars and have forces in a garage, like reprogram it and do crazy things with it. But if you get hired and go to an OEM like the big three, it's pretty well understood once you're in the door how to actually program that. And so they're not hiring a ton of people in that area. The other reason we don't do that, really the more practical reason we don't do that, is it becomes much harder to teach online. When we have 10,000 students that we taught all over the world, it's much easier to teach people all over the world how to do lane finding, how to do vehicle detection, how to do sensor fusion and localization. It's harder to teach someone to get a car and hack the canvas. Cool. Yeah.
So it's our software development migration towards All-Star. The boss and the other tools are those intermediate between the data that they always migrate towards All-Star, the users get across, or how do you train compared to people ready for that mission?
Yeah, so good question. So the question is about AutoStar versus training folks for AutoStar versus things like ROS and AutoWare. So what we teach ROS and AutoWare, we don't even teach a little bit of ROS, we don't teach so much AutoWare, but we use those. Our open source, the automotive industry has historically been very reticent about utilizing open source software. They're much more likely to use proprietary software because then there's a company standing behind it. Somebody can sue if something goes wrong. So AutoStar is an example of a type of proprietary software that companies use to run their self-driving software. I don't have a particularly terrific answer. I think in general, the principles that you learn for message passing and cross, for dealing with for data and cross paths, and then the principles around lane finding and localization and path planning, those all pretty much work wherever you're going to go. A lot of it is about plugging your algorithms into particular modules that might be used by an AutoStar architecture or by a ROS or AutoWare architecture. You don't need to know ROS inside and out necessarily, for example, to run. You simply need to know how to put your algorithms into ROS modules or ROS nodes. And for us, it's just a lot easier to work with ROS and teach students to work on ROS as opposed to sitting up an AutoStar architecture and trying to get that in the hands of 10,000 students around the world. And I do know from talking to some companies that a surprising number of companies, they tend to be more the startup companies or tech companies are running on a ROS architecture. I think AutoStar is probably much bigger in Michigan. In California, we tend to see more ROS.
The ROS people are always being funded by the Department of Defense. Try to make a lot more articles and possible to use one of them to the knowledge of what to do with the sacred and AutoStar is also more of that system AutoStar adapted that close to the tech architecture. And losses like this, they would have more of them getting close together and how they operate. develop for them. That would be provided to these, I think, tools developed for you to use or, and I think there's like a lot closer together at a lot of production and a lot of that. And also, I think he's also the reference to one of the campus and the other side.
When you talk about Ross, I heard you talk about messaging. You see it more like mom, and that is that's part of the
I'm not that familiar with mom, so I couldn't make a definitive statement on how close Ross is to mom. I think of Ross is kind of the canonical publish subscribe system, essentially. Publish to messages that are being passed off to certain nodes, or you subscribe to certain nodes when you get the messages. It was an event-based system. Also, is kind of the term we use. Yeah.
When we're talking about these frameworks, where do you see Apollo fitting into all this?
Yeah, so Apollo is an open source platform that is being developed by Baidu. Baidu is kind of the Chinese Google. They're actually going to be building a fairly short 1-month course on Apollo in conjunction with Baidu. We're really excited about that. I'm interested to see where Apollo goes. I think it's early days. I think having an automotive framework that a company with a lot of money is really putting themselves behind is exciting. I think it could lead somewhere, but we'll kind of see on that option. They have a very long roster of partners, and I think the key question will be what kind of updates they get from all those partners. It's really easy to say, we signed up, we're excited about this. The real where the rubber meets the road is being put this on your own vehicle. It could happen, but it's already example.
Where do you see communication between, say, Carla and a sister or a brother? You know what I mean? Because obviously she would benefit from owning a car a quarter mile up, just ate a deer, went over a pothole, or whatever, all that sort of stuff.
Yeah, great question. So how does Carla communicate with other vehicles in the world, a sister or brother? We're actually thinking about getting a second self-driving car, and so vehicle that isn't alone with vehicle-to-vehicle communication. Jim out on the lab was talking about out in Mcity, was talking about DSRC, which is one of the vehicle-to-vehicle communication protocols. We also referenced this kind of raging debate inside the vehicle-to-vehicle world, which is a very raging debate about DSRC and mesh networks versus cellular. So some people think it makes a lot of sense for vehicles to talk directly to each other and have this network of vehicles that's building their own kind of mesh network, ad hoc communications network between vehicles as they come and go out of an area. And other people think it makes a lot more sense that the vehicles talk directly to the cloud, to the internet, and then talk to each other essentially via the internet. And that's what we use cellular networks or mobile networks to pick up the internet and back down to the vehicle. That's, I guess, there's a little bit of that digression into simply how vehicle-to-vehicle communication might work, and kind of the debates in that world about that. The exciting things about vehicle-to-vehicle communication are the ability maybe to route traffic more intelligently, to make the movement of traffic more efficient. If one car knows when another car is starting, it makes it easier to have the platoons of cars. A few interesting things I've seen in this world, and we'll see kind of, or I've seen in the world, in our world, and we'll see where they go. One is platoon trucking. Peloton, based out of Palo Alto. They have platooning software for trucks, and it essentially works with human-driven trucks. It's not level 4, level 5 software. Maybe it will become that eventually, but it helps human truck drivers form platoons, which they claim can save on the order of about 10 to 20% in fuel costs, because you get essentially a drafting effect if you think about like how bicycle racers draft. Vehicle to vehicle, essentially the one vehicle knows when the vehicle header is going to speed up or slow down. So it's kind of interesting to think about where that might go. And then the first, I think, real commercial OEM grade DSRC or vehicle-to-vehicle communications product out there is some of the work Cadillac has done. So some high-end Cadillacs have some very early vehicle-to-vehicle communication. Essentially, I believe one might come out there 400 meters ahead or 400 feet ahead and do a hard stop, and that'll give some intelligence to the adaptive cruise control system. But it's very early days, kind of exciting to see where it might go. The big bridge across will be like when one manufacturer or supplier's system can talk to another. Right now, the systems are fairly proprietary, and there'll be a lot of progress when it's not just Cadillac talking to Cadillac, it's Cadillac talking to Ford, to Toyota. Yeah.
So what's the kind of on people's
Yeah, that's a great question. We don't cover vehicle-to-vehicle communication in the program right now. We talk off and on with different people, different companies working in the space, and it may be something we add, but it's not something that we have in the simulator that we incorporate into the program at the moment. It's still, it feels like B2B is probably where self-driving cars were about 5 years ago. We'll probably get some level of autonomy first, because you can build a self-driving car kind of by itself. Whereas in order for B2B to make sense, you have to have at least 2 vehicles, and preferably a lot more than 2 vehicles. So it's probably going to be a little longer to get there, but it's kind of exciting to think about where we might get it. And I certainly like to build vehicle content, of course, see what you can.
You said about a lot of percentage of the people who take your course are from Michigan, from this Detroit area. So when I started the course and I was looking for classmates, the Slack channel was dead silent. There was nobody there. Mm-hmm. And then, there's obviously no events around here to sort of network. And then I really didn't understand the mentorship system. And then what happens after you get finish the degree? Is there some sort of, what have you sort of worked on towards the community side of it? That can you explain more on those aspects, like, finding classmates, what do the mentors do, and after you're done, how would you find jobs, or how would you find, employers or projects to work on?
Yeah, those are great questions. So this is kind of a Udacity specific question. You're in the course, and we have the Slack community for Udacity self-driving car students. I think most of our Udacity programs have a Slack community, and the Slack community has different channels. One of the channels is Detroit, which is a little bit quiet, a little quieter probably than the Bay Area or Europe, but we do have a fairly large community of folks here, and people like David and Alex have done, I think, a really nice job of building up the community of folks who are interested in self-driving cars here. One of our communities, we have a team at Udacity, they are the community. Their goal is to kind of build the Udacity community. And one of their big goals for 2018 is local study groups, organizing local groups of people to get together in person and program together. We tried that a few times at Udacity, and it's been a little bit of a struggle to get going because it depends on really on 1 or 2 people to really kind of be the ringleader in a given geographic area and kind of pull everybody together. And when that person either graduates or drops out or moves away, and then things kind of, we're working on ways of doing that more robustly, or at least facilitating students doing that. That is a big focus, but it's something, the in-person aspect, we struggle with. We're quite good at online and not as good with in-person. And as far as graduating, we have an online community. That's a big goal of our alumni teams. We have teams for everything. We have a careers team, we have a community team, we have an alumni team. Our alumni team is trying to grow the base of alumni, help alumni hire other students. One of the things we've been really fortunate about in self-driving cars is many of our students have gone on to other companies, and they often are excited about hiring more Udacity students. They think very highly of the program and of the other students in the program. So we're working more on leveraging our alumni community
one last question.
Yeah.
How valuable is, for urban environments, or rural or whatever, how valuable is footage? I mean, from a machine learning side or whatever, is it? And if it is valuable, how how can one go about getting the millions of miles that one needs without kind of like a crowdsourcing, whatever Pokemon in your celebrity just gives it up for free?
Right. Yeah, great question. So data, how valuable is data? Data turns out to be really, really valuable in this space. Particularly what companies sometimes call interesting data. Driving down a highway and in no traffic, getting data is important, but eventually you have enough data. The real question is how do you get all those millions of edge cases? And there are a few different ways we've seen companies do it. One is to simply throw money at the problem. That's kind of the Waymo approach, right? Like if it's an advantage to go last month of money, they add cars out there longer than everyone. I work in Mountain California, and we actually work right across the train tracks from the Waymo office. And so we've been seeing their cars taking around Mountain View since forever. They've just collected tons and tons of data. And Sebastian, my boss from his time at Google, has all sorts of great videos of like cars driving down the road the wrong way, deer running out into the road, all sorts of crazy stuff of I think Chris Ernsten has a famous video formerly of Google of a woman in a wheelchair driving her wheelchair through the street herding ducks. There's all sorts of crazy things you wouldn't think about. So that's one, is just to simply just have a lot of test vehicles out there. Another is to build something like Mcity. I think Jimmy mentioned that Mcity was the first facility of its kind, and now there are several dozen. I don't know where all those dozens are, but I assume they're mostly proprietary facilities. One by famously has a facility out in the Central Valley of California called Castle, former Air Force base that they leased a large part of and built their own testing facility. There are other facilities, there's one in Korea called K-Town, there's one at the University of Tokyo, and there are a number owned by different other companies. And then there are more creative ways to do it. We've seen Comma AI, which is a startup based out of Silicon Valley, essentially distribute this system for adaptive cruise control in your car, and they're basically giving it away. They've gotten in some trouble with the regulators, or they're kind of open sourcing the software. But all they really seem to care about is the data. They just want to collect all the data. So they'll give you adaptive cruise control in your car for free. You have to have the exact right type of car, and you have to be willing to kind of hack it a little bit, but you can get adaptive cruise control, kind of Tesla autopilot-like functionality, and then what you do after that, if you can call it getting something up, is Comma AI, which you're just tweeted at me actually the other day that they collected 500,000 miles of training data, which puts them somewhere not in the lead, but maybe in the top 5 or 10 companies of miles driven. And they claim that they are going to surpass every company except Tesla at the end of the year. So that's another way. Things like Uber and Lyft, naturally they have lots of vehicles on the road. There's the complications because the vehicles are owned by the drivers, and so there are limits to how much they can practically and legally do to get out of those vehicles. But having a fleet of vehicles at your disposal.
Are you familiar with OfferCam?
No.
So this is something that Alex had picked up a couple months back in the Detroit group, and it's very new, but it's an organization where it's purportedly you use your cell phone video, and they have either prizes or cash theoretically that you can trade, your miles and so on. And whether they kind of make it happen or not, can you even do it with a fleet, or do you, in order to get the requisite footage that you need for all the roads and all that stuff, do you have to come up with some sort of way to get the general public involved? I guess is the question.
Yeah, that's a really good question. Like, can you do it with leaders? Does it have to be kind of getting data from the general public? I think we don't know the answer maybe for sure. What we have seen is the most advanced self-driving systems on the road seem to be getting up, and they've done it basically with a fleet of vehicles. It will be interesting to see if someone can use the Silicon Valleyism to disrupt Waymo by doing something like getting data from a wider fleet. There are companies like Comma that are essentially trying to do that and see what's there.
a regular cell phone from a resolution perspective or whatever, that would be fine? Or is there a technological limitation there?
I mean, you want as much data as you can get, and so with a cell phone, you can get some stuff. You can get, a video feed, maybe not super high res, but maybe high enough resolution. You can get some data off of the accelerometer and some GPS data, but you can't get the super high resolution data that you can get off of a LiDAR-based localization system. With that, you need to tie into the OBD2 port to get things like speed and acceleration. And so the more data you can get by plugging into the car's existing network, or better owning the car and being able to get all the data off the car, the better. You're kind of limited when you're hacking other people's cars, or trying to get other people to hack their cars. Cool. Well, thank you very much for hosting tonight. I had a wonderful time. It's my first time at Mcity. Thank you so much to David and Alex for organizing this, and to Sarah for giving us this tour of the facility. Thanks for the great questions that I asked. And thank you to half of you, I guess, for about who are in the program, some of who graduated of the program. We are really grateful for you guys spending this much time with us. I know it's a lot of time, a lot of effort. Hopefully, you feel like you got something great out of it. Thanks.
Maybe a quick note. So, transition a little bit after that. Thank you, David. You're welcome. I appreciate it. And we started, so to take the knowledge that you kind of saw here today, we wanted to take it a step further. We wanted to do something that has actual application or is a physical item, not just in virtual spaces. So we started working on a little car over here. You can connect your Wi-Fi to it and run your code on it, and try out the things that you learn about. Actually, on screen there is the link finding algorithm, as Rob just pointed out. But essentially, we took what they talk about, and we're trying to use it and get better at it. So if you have any interest, contact David or myself to find out more about the group or join her. Again, thank you for coming out.
They're both on Meetup, and Alex has a Facebook page to try out a motor vehicle group. That's that group's page. So for sure, engage and we talk and get involved. It's quite interesting. It's a lot of fun. Oh, we have a race between the two groups scheduled. Yeah, there is. Someone's called to win. Football tickets if you join the Michigan, the Ann Arbor team.
There'll be California if you win. Right now on the TV.
We have a friendly competition, and you can see the cars. The cars and groups are back here. In the back, we're looking at sometime in the spring to put that on, and we may have it posted over at I3, which is a makerspace in Ferndale. That's the Detroit makerspace. I3, very cool. If you're not familiar with that. And alternatively, maybe we'll graduate the racing here in the city at some point as well. But yeah, we can always use more people that are interested. It's a great environment for everything.
Awesome. Thank you. You're worried about the sound. I worked with the sound and stuff. Yeah.